This talk is on something that I really like doing. Actually, I like all of graph theory. And as we have seen for the past 2 days, there are many interesting areas within graph theory. My favorite is distances between vertices of graphs, and that's what I want to talk about today. And just like the other speakers, I have tried to find a good balance between keeping things elementary, but also mentioning a few of the bigger or more recent problems, showing some recent progress. Nevertheless, I fear I may make you work just a little bit more than the speakers in the past 2 days, because we actually do have 2 or 3 proofs. Okay. Let's go in. Let's get started. Okay, so the first bit is generally on distance, and I want to talk quite a bit, at least for the first part, on distances in general, and also on the diameter and the radius in graphs. So let's say G is a connected graph, and I won't mention it every time that the graphs that I look at are connected. At some point, I will stop just mentioning that, and we assume that. Otherwise, distances don't make as much sense. Okay, so if G is a connected graph, first of all, for starters, so that we are absolutely sure everybody knows we're talking about, the distance between 2 vertices, U and V, is the length of a shortest path from U to V. So a very simple example, the distance in this graph here, the distance from A to C is just 2, because I find a path from A to C that has length 2. I also can find longer paths, but by distance, I mean the length or the number of edges of the shortest path. And then the diameter of a graph is just the largest of all distances. So the diameter is the first distance measure that I want to look at. And by distance measure, I mean just a number that somehow collects all the distances in the graphs in a given graph, summarizes them, puts them into one number that tells us something about a particular aspect. And here in this case, that aspect is that the diameter is the largest distance. So all other distances all distances in this graph are less or equal to this number, and the largest is actually equal to this number. Okay, so here in this particular example, the diameter of this graph is 7. If you check the distance from A to B is 7. You won't be able to find a shorter path from A to B. That's why the distance, but you will find a path from A to B, for example, going along the bottom of the graph and then up, of length 7. And the distances between all other vertices are exactly 7. Are at most 7. So that is the largest of the distances. Okay. Now let's assume that G is a connected graph. Let's define something else. Let's define the eccentricity of a vertex, and that's simply defined as, if we have a vertex, let's say U, then the largest of the distances from U to any other vertex in this graph, that's what we call the eccentricity of vertex U. So I've written it here as a formula. The eccentricity of U is the maximum over all vertices T of the distance from U to T. Okay, so that's the distance to the vertex furthest from U. So in a way, the eccentricity tells us how far do we have to work from this vertex U to any other vertex in the worst case. So if we go back, vertex C here, in this case, has an eccentricity of 5, because it happens, as it so happens, vertex B is at distance 5 from C, but all other vertices are at distance less or equal 5. That's why the eccentricity of that vertex is 4. And the smallest of all eccentricities, that's called the radius. Okay, so again, in our graph a moment ago, if we pick vertex D, we will find vertex D has eccentricity 4, but you won't be able to find a vertex with eccentricity 2 or 3 or anything less than 4. That's why the radius of our graph is equal to 4. And a good way to picture the meaning of these notions, diameter, radius, and eccentricity, is if we just draw a circle here, then the diameter is just the longest distance between 2 points of the circle. The radius is the distance from a point in the middle to the actual circle. And the eccentricity of a point, well, it's stretching it a little bit, but that's if we pick a point, the distance to the point furthest. That's what we call eccentricity. And I want to talk a little bit about what we can say about the diameter of a graph or the radius of a graph if we have only limited information on the graph. So for example, let's say if we know the diameter, what can we say about the radius? If we know the number of vertices, what can we say about the diameter or the radius, and so on. Let me start with one very famous relation which holds not just in graphs. So people who work more in topology will have seen things like this. And that's the famous theorem, let G, if G is a connected graph, then the diameter is always between the radius and twice the radius. Well, let's quickly prove that because that's so easy. Certainly the diameter is the largest distance, the largest of all distances, and that means it must be greater or equal to the distance to the eccentricity of any vertex, because that's just the largest distance from this vertex. Okay, and on the other hand, the diameter cannot be more than 2 times the radius. And the reason, I've written it down here, but it's easier summarized in words. If you have any 2 vertices in the graph, then it's easy, or one way to get from these vertices, let's call them A and B, to go from A to a vertex whose eccentricity is the radius. That will take you at most R steps, or that will be a path of length at most R. And then from there to go to vertex B. That will take at most another R steps. So in total, you have, that gives you a route from A to B via a radius vertex whose length is at most twice the radius. And possibly you can do better, possibly not. But that tells us about this relation. And it turns out that we can give better relations for certain graph classes. So for example, for trees, I'm not going to go into details yet, but that's one thing that you will find quite often also in the course of this, as we go along in this lecture, that we can say something about general graphs, but then about special graphs like trees or other graphs, we can say something a little bit stronger. Okay, but I will be talking not only about graphs, but also about digraphs, that is directed graphs, in which every edge has a direction like a one-way road. And there, the distances are defined in exactly the same way. The distance from a vertex A to a vertex B is just the length of a shortest path from A to B. So here, I've taken a similar graph, except that every edge now has a direction. And looking at, for example, vertices C and D, we immediately notice one thing that that shows that the distances in digraphs are quite, or can be quite different from distances in graphs. That's that the distance from C to D, if this, well, is clearly 1, because we can go from C to D in one step. But the distance from D to C, which in an undirected graph would be the same, but in a directed graph where each edge has a direction, it's not that easy. We can't go directly from D to C. We would have to take a detour up and then fully to the left, then down, and then again to the right to C. And that distance turns out to be 7. So the distance from C to D and the distance from D to C are quite different, and that's not unusual for digraphs. Okay. Also, just like for graphs, I said I look only at connected graphs. We will always have a path between any two vertices. We will also look here only at strong digraphs, where strong is really the abbreviation of strongly connected digraphs. And by that, we simply mean that if you pick any two vertices A and B, there will be a path from A to B, but also a path from B to A. Just like we had here, there's a path from C to D in that example, but there's also one longer, unfortunately, but there is a path from D to C. We will consider only those paths. I will not mention it every time. And we will also look at the diameter, in other words, the largest distance between two vertices in a digraph, and see what can we say there. And one tiny little remark about one trick that we will apply a few times, and that throughout the research on distances, one applies that really every day. It's like a bread and butter trick. And that's the idea that if you want to prove an upper bound on distances, like on the diameter, the radius, then if you take your graph and you remove an edge so that the remaining graph is connected, no distances can go down. Distances cannot be shorter if we remove edges from a graph. It may even destroy paths and make some distances longer. It can't make distances shorter. And for that reason, one can often, for example, if one want to show something about distances in a graph G, take a spanning tree, which is just a graph that we get by deleting possibly quite a few edges from G, and then prove whatever we want to prove for the spanning tree, and then argue, well, if it holds for the tree, in which the distances are not smaller than G, possibly bigger, then whatever we want to say will also hold for the distances in G. Okay, so let's quickly start with really elementary bounds. And these bounds are on distances, the first one is on the diameter. And that's something that is really quite easy. If I have a connected graph or strongly connected digraph with n vertices, how large can the diameter be? And the answer is, well, it's certainly at least one, provided you have two vertices, then you will have a distance 1, and that could theoretically be the largest one, can happen. Or the worst, largest that can happen is that the diameter is n-1. And to see that, you can just argue that, well, if I pick any two vertices, the path between these two vertices will pass through, well, at most n vertices, and that means if I count the two ends of the path as well, these two vertices that are connected by the path. So my path from the one vertex to the other has at most n vertices, and that means it has at most n-1 edges. So that's why no distance can be greater than n-1. And here are two examples that do that. Here's a complete graph. That graph has diameter 1. Any two vertices are adjacent, any distance is equal to 1. Also, the diameter is equal to 1. Which graph has the largest diameter? Well, that's pretty easy. If you didn't know it, you could probably easily guess it. It's the path. And if you take a path, that's the graph in the middle, then a path from the leftmost vertex to the rightmost vertex would go, if we have n vertices, this path would go through all vertices, so it would pass through all n vertices of the graph, and it would have length n-1. So the distance between the two ends of the path is indeed n-1, and that's the diameter of this graph. And we can also have a diameter of n-1 in a digraph. It can also happen that path has to go through all vertices. One example for such a graph is a directed cycle. If I want to go from the top vertex to the vertex that's here roughly at, let's say, 2 o'clock, so on the right, I have to go through all the vertices of the path. And if my directed cycle that I have here has n vertices, this path will have length n-1. If we explore that a little bit more, we will again find another difference between graphs, undirected graphs and directed graphs here, because if I want to draw a graph, an undirected graph with diameter n-1, there's only one choice. This path is it. There is no other graph. But it wouldn't be very difficult to draw lots of quite different looking digraphs that have n vertices, but whose diameter is n-1. Okay, let's look at the radius. So the diameter is really easy and a nice warm-up. What can we say about the radius if we have a connected graph of diameter, a connected graph with n vertices, and let's say n is greater or equal to 2. Then the radius of G, that's what this theorem says, is between 1 and at most the floor of a half n. Okay, well, that the radius is at least 1, that's again clear. If we have two vertices, there must be a distance that's 1 from any vertex. So, and we have 1, of course, if there is a vertex that's adjacent to every other vertex in the graph, like in the picture on the left here. The upper bound here, a half n, is attained by the path or by a cycle. These are, depending on the parity of n, the only possibilities. Let's prove it. And here I will do one thing that, you will see a few times. I like proving things approximately. In other words, be a little bit sloppy, a little bit rough, and maybe prove a result that's not exactly what I claimed, but really close to it, simply because it allows me to show a few nice pictures. So let's do that. Let's prove that the radius in a graph with n vertices is at most approximately half n. And I do that in 2 steps. First, I prove that this theorem holds for trees, or this bound holds for trees. And then I will use that to show that it holds for every connected graph. So that's a trick. Again, that's my bread and butter trick. But trees are nice because they've got nice properties, for example, end vertices. Okay, so step 1, let's prove the theorem approximately for trees. So what do we need to show? We need to show that in our graph, we are guaranteed to have an eccentricity, a vertex whose eccentricity is at most n over 2. If we have that, then we know that the smallest eccentricity in the graph will be less or equal n over 2. Certainly, if our graph has just one vertex, then this holds. Then the radius, well, then our graph is just, well, don't blink, you miss it, otherwise, this one vertex, K1, and that even has an eccentricity of 0, because the distance from this vertex to every other vertex is 0, because there is no other vertex. It's only itself. Well, if we have 2 vertices, then this is what our graph looks like. It's K2 and its radius is certainly 1. Pick any of the 2 vertices and its eccentricity will be 1. So let's assume that our graph, our tree has at least 3 vertices. Then, and because it's a tree, let me call it T. I like calling trees T, otherwise I get confused and I'll keep looking for a cycle. So let's say our tree T has at least 2 end vertices. And just so that I can use it better in a moment, let me call this tree not T, but T0. And then I'll do something, and I'll repeat that a few times. I remove all end vertices of T0. Then I get a new tree, T1. Then I take T1, remove all end vertices, I get a tree T2. And then I remove again all end vertices. I keep doing that until I get a graph, let's call it TK, that has only 1 or 2 vertices. So let's look at a picture here. There is T0, that's the graph I start with. I remove all the end vertices. Then I get T1, which has only 4 vertices left. And From that graph, I again remove vertices, the end vertices, and I get my graph T2. Okay, and that's a graph with just one vertex. That's where I stop. So my K would be 2 in that case. So, and let V be a vertex of the last graph TK. So in this case, it would be this blue vertex. So I want to check what happens to the eccentricity of V, of this vertex, of the blue vertex here. In the last graph, in this case, it's 0, but I said I do this until I have only 1 or 2 vertices left. So if I have 2 vertices left, then the eccentricity in the last graph of the blue vertex could be 1. So the eccentricity of V in the last graph is less or equal 1. The eccentricity of this blue vertex in the graph before it will be at most 1 more, simply because I have attached a few end vertices. That means the furthest vertex, or a furthest vertex from the blue vertex, could now be 1 step further. And that means the eccentricity, if I go back to T1, of the blue vertex could have gone up by 1. And then if I go 1 step back, the eccentricity would have gone up by at most another 1, and so on. So my eccentricity of the blue vertex in TK is 1, in TK minus 1 is 2, in TK minus 2 it's at most 3, and so on. And in my graph T naught, the eccentricity of V is at most K plus 1. Okay, now I just have to think quickly, how large can K be? But that's actually quite easy, because in every step I removed at least 2 vertices, because every tree, unless it has 1 or 2 vertices, every tree with 3 or more vertices has at least 2 end vertices. So at every step I removed at least 2 vertices, and that means that K is about at most n over 2. Well, if you think a little bit more, it's at most n minus 2 over 2, and approximately this gives us the theorem. We just put this bound for the K in and get that the eccentricity of V is about at most n over 2. If you want to prove the precise value with the floor, you have to check things a little bit more carefully, but the idea remains the same. Okay. So now we have proved this theorem for trees. How do we prove it for all connected graphs? Easy. We just pick our graph G, take any spanning tree that we like, and then we know that for this spanning tree, which has n vertices, the radius is at most half n, and that means that the radius of G, which is less or equal to the radius of T, because as we said, distances in G cannot be larger, they can be only equal or smaller than the distances in T, then the radius of G will be at most half n. Okay, and since I've shown you this trick with removing end vertices, let's just prove another really simple theorem to warm up. So what if we know something more about our graph than just the number of vertices? And one of the things that many people like looking at is the vertex degree. So for example, if our tree or if our graph has a vertex of large degree, big delta, can we find a better bound? The question is quite natural, because we said that the worst radius is attained if our graph is a path or a cycle, and that means its maximum degree, its largest degree is 2. What if the largest degree is a lot bigger than that? And I claim that we have the bound that the radius is at most n minus delta plus 2 divided by 2. So there's this little delta in there. Okay, and this proof is very easy if we apply the same trick, but we won't repeat the whole thing. We just think what happens in the first step if we have it. So we first prove our theorem for trees. If we remove all end vertices, well, we hopefully, or we may have learned in a graph theory lecture, that if we have a tree with maximum degree delta, then this tree must have at least big delta end vertices. So let T prime be the tree obtained from T by removing its end vertices. So that's exactly what we did just a moment ago. Then the number of vertices of T prime is the number of vertices of T minus delta. But the eccentricity, so they differ in delta, the number of vertices differs by delta, but the eccentricities of the two graphs, or the radii, differ by only one. So if we, to do that more formally, let's look at T prime. T prime has at most n of T minus delta vertices. Then T prime must contain a vertex whose eccentricity is at most n minus delta over 2. And this very vertex, if we look at that in T, its eccentricity is one bigger, and that's at most n minus delta plus 2 over 2. And that gives us our theorem for T. And to recover the theorem for all graphs now, that's easy. We just say, well, if we have a graph G, any graph with maximum degree delta, then we can easily find a spanning tree T with the same maximum degree. And to that graph, we can apply step 1, and we get that the radius in G is again at most n minus delta plus 2 over 2. So we do the same as we did a moment ago. Radius of G is less or equal to the radius of the spanning tree T with maximum degree delta, and that's at most the desired bound. And we can do something similar for the diameter. And here, that's even a lot simpler than for the radius. We can just argue if we have a vertex of large degree, like for example in this example here, any shortest path between two vertices will go through at most two vertices, at most two neighbors of the vertex of maximum degree. And that means delta minus two vertices definitely won't feature in the shortest path. And that means the diameter, any shortest path has at most n minus delta plus two vertices, and therefore length at most n plus 1 minus delta. And that's sharp. Okay, things get a lot more interesting if we say, well, okay, let's move away from trees. What if we know the minimum degree of our graph? Well, the minimum degree for trees is not very interesting because it's always 1. But what for other graphs? And that was a question actually that people got quite interested in a pretty good while ago. The first one in 1965, and then various teams of authors, and I'm not absolutely sure that my list here is complete, proved a result or slight variations of that, which says that if we have a graph with minimum degree delta, then the diameter of G is bounded by 3n over delta plus 1 minus 1. Okay, so what's the big difference to the bounds we saw a moment ago? N, the number of vertices, now in this bound has a coefficient of 3 over delta plus 1. So for example, if we have a minimum degree of 3, then the diameter can be at most 3/4 n minus 1. And this bound, if we don't pay too much attention to the additive constant, and if we don't care whether this one is just right, this bound is then actually sharp. But to see an example for sharpness, well, it's a graph that I've drawn here, or I've tried to sketch it here. It's a graph with minimum degree, in this case, with minimum degree 3, that looks as close to the path as you can get if your minimum degree is 3. So the path is the longest of all graphs of given order. And this graph that I've drawn here is really the longest of all graphs with minimum degree 3. And how do I do that? I take a K4 minus an edge, and the edge that I've taken out is the edge between the left and the right vertex of each K4. And then I string them up to form something long path-like. And at the end, well, at the very end, I may have to do something slightly different to make sure that every vertex really has degree at least 3, but that's basically what this graph looks like. And I can make this as long as I like. And each of these little K4 minus E has obviously 4 vertices, and it increases. If I put one more of these boxes here, it will increase my diameter, which is the distance from the very left to the very right, by 3. So by adding in 4 more vertices, I will increase the distance by 3. And that's why I have a diameter of about 3 over 4. And this works not only just for delta equals 3, I can do that generally for any delta. I just have to replace the k4 minus e here by k delta plus 1 minus e. So for example, if I wanted to have minimum degree 5, in my box I would put a k5 minus an edge, and the edge is the one joining the leftmost and rightmost vertex of that. Okay, let's quickly prove that result. Because the proof is so short and elementary, I thought I'd put it quickly in as well. So let's say we call the diameter of our graph d, and we have a graph with n vertices, minimum degree delta. So we know every vertex is at least degree delta. So let's pick 2 vertices. Let's look at the picture. Two vertices, v0 and vd, whose distance is equal to the diameter, which we call little d. And let's look at the shortest path between them. Then what I do is I look at every third vertex on the path. So if I number my vertices v0, v1, v2, v3, v4, v5, and so on up to vd, then I look at v0, v3, v6, v9, and so on, as long as I can. I may not be able to catch the last vertex, but we can still get our bound. Okay, then I look at the closed neighborhood of each of these vertices. So for example, the closed neighborhood of v0 and the closed neighborhood of v3. And the important point here is these 2 sets, the closed neighborhood of v0 and v3, are disjoint. If v0 and v3 had a closed common neighbor, then I would be able to get from v0 to v3 already in 2 steps. But I do need 3 steps because I picked the third vertex of my path. So similarly, the closed neighborhood of v6 is disjoint to the previous 2, and of v9 is also disjoint to all the ones before. So these closed neighborhoods are all disjoint. And how many closed neighborhoods do I have?
Sorry to interrupt, Prof. I accidentally muted you there.
Oh, okay. I see. No problem. Yes, has that been for a long time? Should I go back for a second, or was it just for a moment?
I think it was about 4 seconds maybe. So I think maybe it'll be best to just restate that. Thanks.
Yeah, thanks a lot. Thanks for alerting me. Okay, so the whole point is we pick every third vertex, and v0, v3, v6, v9. And because we pick every third vertex, these vertices v0, the closed neighborhood of v0, and the closed neighborhood of v3, and the closed neighborhood of v6 will all be disjoint sets. Again, the reason is if, for example, v0 and v3 had a common neighbor, then I would be able to get from v0 to v3 in 2 steps. It was 2 steps through the common neighbor, but the distance must be 3 because I picked every third vertex. So what I have here is I picked about d over 3 vertices, roughly, and each of these gave me a set of at least delta plus 1 vertices, because my minimum degree is delta, and I count the vertex v0 itself in the closed neighborhood, or the vertex, each vertex. So I've got about d over 3 disjoint sets, each with delta plus 1 vertices, and that tells me that n is greater or equal approximately d over 3 times delta plus 1. I've written it here a little bit more precise, but if you take that and you just solve it for d, you get that 3n divided by delta plus 1 is greater or equal to the diameter, which is precisely what we wanted to prove. Okay, let me skip this little bit, otherwise I may run out of time. Let me just come to the bottom result. Yes, I realize I would go a little bit over time if I if I speak too much on the other things. Yes, perhaps let's just look briefly at the sharpness examples here. In this sharpness example, if we pretend for a moment that this is the only one, we have lots of graphs, subgraphs that are almost k delta plus 1, where k delta plus 1 minus e. But if delta is like greater than 3, then we will find all sorts of subgraphs in it. Triangles or 4 cycles or smaller subgraphs, smaller complete subgraphs, cliques, as long as they have fewer than delta vertices, and so on. And that suggests one thing, that if we look at graphs which do not contain certain subgraphs, for example, that do not contain triangles, or that do not contain 4 cycles, which are all in this extremal graph that I've shown you in abundance. But if a graph doesn't have that, then there is a good chance that we can improve the bound that we have here quite a bit. And that's been research that's going on quite a bit. For example, in their paper, Erdős and other people, Pachpolak, Tuja, proved that we can improve this bound for triangle-free graphs by about a factor of 2/3. If our graph is C4-free, we can even improve our bound quite a bit from something times n divided by delta, which we had a moment ago, to something times n divided by delta squared. And just to show you that this is also something that we are working on right now. So here's a result by Alex Aluchukwu, who showed that this Erdős bound, if our graph doesn't have only no 4 cycles, but also no 3 or 5 cycles, then we can improve this bound even by another factor of 3/5. So the diameter is at most 3 over delta square plus some small change times n. Okay, and one can do that, and that has been done for lots of similar graphs. And similar bounds to these ones can also be found for the radius. However, for that, and these bounds are typically about half the bounds of the diameter. But to show you how that's done, I would need a little bit more time. So I thought, let's rather look at other interesting things. And one of the questions that I want to look at is the question, well, do these bounds also hold for directed graphs? Because I've now spoken on undirected graphs and order and minimum degree. Do similar bounds also hold for directed graphs? So just to go back, we had here for the diameter, if we know in an undirected graph, we have 3 over delta plus 1 times n. That's an upper bound on the diameter of an undirected graph. Is something similar true for directed graphs? And Suarez showed in 1992 that no, this is unfortunately not at all the case. He constructed graphs, which are not very difficult to construct, where, digraphs that have n vertices and minimum degree delta, so the smallest of the out and in degrees, is, so each vertex is adjacent to at least to and from at least delta vertices. And the diameter is only n minus about 2 delta. The point is, he gave examples in which we have minimum degree delta, but unfortunately there's no factor, no coefficient in front of the delta. So for example, for minimum degree 3, if we have 1,000 vertices, a moment ago, we got about 3/4 n. So diameter would be at most 750. But for digraph, we would get only 1,000 minus 6 plus 1, so 995. And if our order is bigger, we would our bounds would always be pretty close to n, which is fairly trivial. Well, what he really wanted to show is not that this is an exciting bound, but that you can't really do much better than this trivial bound. However, Suarez observed something quite exciting, because he showed if our digraph has a particular property, then actually the bound on the diameter that holds for graphs also holds for digraphs. And this property is that the digraph is Eulerian. So when is the digraph Eulerian? When its out degree and its in degree, also for every vertex, the out degree equals the in degree. So if a vertex has out degree 3, it must have out degree 3 as well. And Suarez proved that if our graph is Eulerian, so if for every vertex in degree equals out degree, then exactly the same bound that we have for the diameter of a graph of given order and minimum degree holds also for the directed graph. And to be fair, I need to mention that Kniazev found this result in 1987 too. He unfortunately published it in a Russian journal, which were not always, or for many years, were not easily accessible. And he used a very funny name for Eulerian digraphs. He called them semi-symmetric digraphs, which didn't make it easy to find that paper. In fact, I stumbled across it only when I was looking for something altogether different. Okay, so why is this quite exciting? I find this exciting because this shows that that this bound on the diameter doesn't hold just for graphs, but it holds for a large class of digraphs that actually contains all graphs. And why do I feel that the class of all Eulerian digraphs contains all graphs? Because if I have given any graph, let's take this tiny graph with 3 vertices here, I can turn it by, if I replace every edge by 2 directed edges in opposite directions, I get a graph that is a digraph that is Eulerian, because the in degree equals the out degree for every graph, because for every edge I put in a vertex, an edge that goes into a vertex and out of the same vertex again. So if I view every graph as an Eulerian digraph, then this shows that this bound that we had a moment ago holds for a large class of all of digraphs that contains all graphs. Okay, so this this bound was I thought quite interesting. So and it raises quite a few questions. One question that we explored when many years ago, that was probably 16 years or so, when I visited my old supervisor in Germany. One question that we got interested in is, well, this bound holds for all Eulerian digraphs. So for every vertex, the in degree must equal the out degree. So we were wondering, can you give perhaps bounds that are a tiny bit weaker if we relax the condition that our digraph is Eulerian? So what, for example, if we say let D be semi-Eulerian? That means we allow that for 2 vertices, the in and out degree are allowed to differ by 1. It can't happen only for 1 vertex, but this is like the tiniest possible deviation from being Eulerian for a digraph. If you say for all vertices with 2 exceptions, we want all in degrees to be equal to the out degrees. And what we firmly expected was that we get the same bound, just the additive constant here, the -1, would be something slightly different. But we were very surprised when it turns out that actually the coefficient 3 over delta plus 1 changed. So by just allowing 2 exceptional vertices, the coefficient of n changed from 3 over delta plus 1 to 3 over delta plus 1 minus delta minus 2 over 3 delta minus 5. And this bound is actually sharp. And if we allow more exceptional vertices, to be precise, 2 as exceptional vertices, then we get a similar bound, but that's not always sharp. That depends on exactly on how S and delta plus 1 are related on divisibility and so on. Okay, let me skip that in the interest of time. I want to stay a little bit longer with Eulerian digraphs. And I want to look at an Eulerian digraph and undirected graph in connection with the diameter and the number of edges. So I want to look at a problem that's quite harmless and that was solved half a century ago. And that's the question, if we have a graph with n vertices and diameter d, how many edges can our graph have at most? That's quite a useful bound, because if you get this bound, you solve it for d, then you will get a bound on the diameter in terms of order, number of vertices and number of edges. Okay, and for that, let's say we have such a graph with n vertices, diameter d, and let's say u and v are two vertices at diameter d, so at maximum possible distance. Sorry, two vertices at distance d. And I've drawn a picture here. These are the two vertices u and v. Their distance is equal to the diameter. And now I want to look at the set of vertices at distance 1 from u. I call that n1. The set of vertices at distance 2 from u. I call that n2. The set of vertices at distance 3 from u. I call that n3, and so on. And in Node, for example, that set contains just vertex u. And the set nd, in this case n6, contains vertex v. It could theoretically also contain other vertices, because v doesn't have to be the only vertex at distance d. So now the key observation is that that edges in this graph cannot just be anywhere. They cannot join any two vertices. So for example, there cannot be an edge joining vertex u to a vertex in n2, because that then we would get in one step from u to a vertex in n2, and then in d minus two further steps, we would be able to get to nd. Or to put it, or for example, there can't be an edge from a vertex in n1 to a vertex in n4, because otherwise that edge would give us a shortcut from vertex u to this vertex in n4. Okay, so edges can only be between two vertices that are in the same ni, or an edge can join two vertices that are in adjacent ni, so in ni and ni plus 1. And that immediately gives us an upper bound on the number of edges that we can have in our graph. And let's call the number of vertices that we have in this set big Ni, let's call that little ni. So how many edges can we then have at most in our graph? Well, we can have, let's first count the edges that we have that join a vertex in some set Ni to the set Ni plus 1. So for example, between n0 and n1, the number of edges is at most n0 times little n1. The number of edges joining a vertex in n1 to a vertex in n2 is at most n1 times n2. And so on. Between n2 and n3, we can have at most n2 times n3 edges, and so on. And if we add all of this up to nd minus 1 times nd, we get the total largest possible number, or we get an upper bound on the total number of edges that join a vertex to a vertex in an adjacent set Ni. And how many edges can we have within an Ni? Well, let's look at n1 that has 3 vertices, and the number of edges joining 2 vertices in the set is clearly at most n1 choose 2. The number of edges joining 2 vertices in n2 is at most little n2 choose 2, and so on. So the total number of edges joining 2 vertices in the same set Ni is therefore little n0 choose 2 plus little n1 choose 2 plus little n2 choose 2, and so on up to nd choose 2. And now we do a very, very simple trick. We notice that these ni are not entirely arbitrary. They satisfy that all these ni are greater or equal to 1, and that their total must be n. the total number of vertices in our graph. And then we ask ourselves, okay, so for which choice of the numbers n0, n1, and 2 up to nd that maximize these, that satisfy these conditions, that all these ni are at least 1, and they add up to n, how can we make this blue term here on the right-hand side as large as possible? And that's quite easy to see, because these terms n0 choose 2 and 1 choose 2, they're all quadratic. It's very easy to guess that we want one of these ni choose 2 to be as big as possible and the other ones as small as possible. So in other words, this is maximized if all ni equal 1, with one exception, and that one contains all the remaining vertices. So that one is equal to n minus d, total number of vertices minus d. And a graph that corresponds to this choice would be a graph like this. Here I packed all the vertices in the set N1, joined them all to each other, joined every vertex to the vertex in the next layer. So for example, the vertex in N0 to all the vertices in N1, all the vertices in N1 to the single vertex in N2, and so on. And that gives me a graph that where the number of edges equals exactly the maximum that I attained a moment, or that I got a moment ago when I said that this bound is maximized if all the ni are equal to 1. They have the smallest value, but 1 has the biggest possible value. So that was, well, that's all old stuff, but this trick is actually quite useful because it allows us to prove similar bounds under additional conditions. For example, if our graph is too connected, well, then the condition on the ni changes, because if our graph is too connected, meaning removing one vertex can never disconnect the graph, well, if that's the case, then we can't have one of these sets, big Ni, with having only one vertex, except possibly the very left or rightmost. For example, if N3 in this picture contains only one vertex, removing it would disconnect the graph. So if I want to have a two-connected graph, I would need two vertices in each of these rectangles of these sets in I. And I get a very slightly different and stronger bound. Okay, so well, that's old stuff. That was discovered really half a century ago. And we can do exactly the arguments, the same arguments for directed graphs. And I've written down the bounds that you get if you do the actual calculations, the number of edges in a graph with order n and diameter d is at most d minus 3 plus n minus d plus 2 choose 2. And for a digraph, we get the same number plus an extra term of n choose 2, which is, of course, a whole lot. Why is that? Well, let's look at this picture of this digraph. I can take the same graph that I have here that looks like a graph of diameter 1, 2, 3, 4, 5, 6, in which the distance from the left end to the right end is 6. And this graph has, for this diameter and this number of vertices, the largest possible number of edges. If I turn this graph into a digraph by replacing each edge by two directed edges in opposite directions, as I've done here, then I can do even more. I can add all possible edges, which I've indicated in blue, joining any vertex, a little bit on the right-hand side, to any vertex that's further on the left-hand side. Why can I do that? Because it will still keep my distance from this leftmost vertex to the rightmost vertex to be exactly 6. It won't provide me with a shortcut. So the moral of this is that for digraphs, the bound that we get here is really a lot worse than for graphs. But the reason I mention this is for Eulerian digraphs, we can actually do much, much better. For Eulerian digraphs, using similar methods, we managed to prove that the number, sorry, that should be D, the number of edges of an Eulerian digraph of order n with n vertices and diameter d is at most 2 times d minus 6 plus n minus d plus 2 times n minus d plus 1. And if you have a brilliant memory, then you will notice that this expression here is precisely twice this bound on the maximum size of graphs. And that means it generalized this bound on the size of graphs of given diameter and order, simply because I can do what I did earlier on. I can, if I have given a graph, I can replace it, or I can, by replacing every edge by two directed edges in opposite directions, I get an Eulerian digraph whose number of edges is twice as big. That can be at most this term, and that tells me immediately that the original number of edges must be at most that what Ore proved, the bound that we had a moment ago. So again, this is a nice generalization of a result on the diameter of graphs that holds for a large class of digraphs, for all Eulerian digraphs. And in fact, it turns out that under all sorts of additional conditions, so if we prescribe not just order and diameter, but also connectivity, minimum degree edge connectivity, then we will get precisely the same result. So we managed to prove that in a somewhat general setting, that such bounds under certain conditions always general, such bounds on the maximum size of graphs for given order, diameter, and other conditions always generalize to Eulerian digraphs. And Mafunda proved that if we have bounds for bipartite graphs, then they also automatically generalize under mild condition to bipartite Eulerian digraphs. Okay. Let me move to another topic, and that's the average distance in graphs. Okay, so a moment ago we spoke a lot about the diameter, a little bit about the radius, but certainly a lot about the diameter, which was the largest of all distances between vertices in a graph. But depending on which aspect of the graph we are interested in, it may be more relevant for us to know not just the largest distance, but to know, for example, what is a typical distance like? So what would be the average of the distances? So ignore the outliers, the few pairs of vertices that have very large distance, but what would be on average the distance between two vertices? And that value is exactly the average distance. I like the name because it says exactly what it is. The average distance of a graph is the number you get if you add up the distances between all n choose 2 pairs of vertices and divide it by n choose 2. So you just take the average of all possible distances. And that has been worked on quite extensively, not always under the name average distance. Other names are used as well. Most people nowadays like working on something very closely related, where they say, well, let's not take the average of all distances, but the sum. And that, of course, amounts ultimately to the same thing, because you just, in order to get the average, you can take the sum and you just divide it by n choose 2. So if you look at graphs of the same order, these two values are practically the same thing, simply because they differ just by a factor. Okay, but here, let me talk mainly about the average distance. And just to get the definition totally straight, here is a small graph. What's its average distance? Well, we find 3 pairs of vertices that are at distance 1. The first and the second vertex, second and third and fourth vertex. We also find 2 pairs of vertices that are at distance 2 and 1 pair of vertices that are at distance 3. If we add all of these, 1 plus 1 plus 1 plus 2 plus 2 plus 3, and divide it by the number of pairs, which is 6 in this case, we get a value of 5/3. So that tells us that the average distance doesn't have to be an integer. It may well, and it often is, just a fraction. Okay, so people have been working on this, in particular on the Wiener index lately, like mad. if I wanted to count the number of papers that have appeared on the Wiener index, I would certainly get to a 4-digit number. God knows it may even be a 5-digit number. And the reason is, the Wiener index is something that was actually introduced by a chemist, Harold Wiener, more than 60 years ago. And he had the brilliant idea of trying to predict chemical or physical properties of compounds. Well, compounds, let's say, by just drawing the molecule as a graph, with the atoms and the bonds, and then analyzing this graph. For example, looking at its diameter, but specifically what he did is he looked at the sum of the distances, and from there trying to derive things like the melting point or boiling point and other things. That was an extremely clever idea, and people have worked on this a lot. So that's why you find a lot of these papers in chemistry, but the more mathematical aspects, of course, are really looked at more by graph theorists. But other people like sociologists are also interested in that, or biologists, or people in operations research, simply because in sociology, if you have a group of individuals and you join, well, for each individual you have a vertex, you turn that into a graph by joining two vertices if they, as individuals, they are friends, then the distances in the graph, in particular the average distance, tell you something about how closely knit this particular group of individuals is. Okay, so let's look at a few bounds on the average distance. And I want to prove, first of all, a lower bound. Sorry, there we are. I want to prove, first of all, a lower bound. The reason is, well, clearly a lower bound on the average distance is 1, because the distance between two distinct vertices is at least 1. But we can have that equal to 1 only if the graph is complete. And if we want to have our average distance to be really small, we clearly need a lot of edges. So I want to know if we know the number of vertices in our graph, and it's n, and the number of edges in our graph, and that's m, what is the smallest average distance that we can possibly get? And here's the answer. The smallest average distance that we can possibly get is 2 minus 2m over n minus 1. Let's do the proof, because the proof is really nice and short. So we have n choose 2 pairs of vertices in our graph, unordered pairs. Okay, of these n choose 2 pairs vertices, we know that m pairs are at distance exactly 1. Those are the pairs of adjacent vertices. We know we have m edges, so we have m pairs of adjacent vertices. For the remaining n choose 2 minus m pairs, we know that the distance must be at least 2. So we have a lower bound of 2 for all other distances. Now put these together. M distances are equal to 1. N choose 2 minus m distances are at least 2. Add them all together, divide by n choose 2, and you get precisely the bound that we have here. And this bound is actually surprisingly useful because it helps you to find lower bounds on the average distance of all sorts of graphs from different classes, where you know the size or the largest possible size. Let's take, for example, trees. In trees, we know that the size will always be n minus 1 if we have n vertices. So that will give us immediately a lower bound on the average distance of a tree in terms of the number of vertices. And this bound turns out to be sharp, actually. Okay. So what's the largest possible average distance that we can have? If I ask you to guess which graph is really the worst, with the largest possible average distance, if I just tell you it must have n vertices, I think within seconds, most of you would tell me that it must be the path. And that's indeed true. And the average distance of a path with n vertices is n plus 1 over 3. So a well-known theorem proved by many people. I couldn't fit in all the names, that's why I didn't put it in, but it's really more an observation. Says that the average distance of a graph with n vertices is at most n plus 1 over 3, and that we have equality if and only if our graph is the path. And I leave this proof as an exercise, so I don't know if Prof. Irwin will want you to do it or go over it. I will be eager to watch that later. If not, try it. I don't think it will take you more than 1, at most 2 cups of coffee or tea, depending on your preference, to do that. It's really nice and easy proof. Okay. So what about other bounds if we know a little bit more about the graph than just the number of vertices and edges? By the way, one bit that I skipped is if we know number of vertices and number of edges. There's also an upper bound, but that's a little bit harder to prove, and in favor of other things, I left that out here. Oops, that I didn't mean to do. So what if our graph is too connected? So if removal of any vertex does not disconnect our graph, well, that certainly disqualifies the path from consideration. So if we have a too connected graph with n vertices, then, well, if I asked you to guess again among all two connected graphs, which one has the largest distances, you probably won't find it too difficult after trying a little bit to guess that a cycle is really the two connected graph with the largest distances or largest average distance. And that's true. And its value is about 1 over n times the floor of n squared over 4. So it's roughly n over 4. While for the path, it's about n over 3 roughly. And because the proof is quite instructive and it gives us or shows us techniques that are also used for other proofs, I wanted to show this proof quickly. So let's take a two connected graph and let's look at the set of, let's pick a vertex V, any vertex now. And let n1 be the set of vertices at distance 1 from V, and 2 the set of vertices at distance 2 from V, and 3 the set of vertices at distance 3 from V, and so on, up to D, if that's our diameter. And a node, of course, contains just the distance V, which is the only vertex at distance 0 from V. Okay, so what I want to do is I want to bound just the contribution of V to the sum of all distances. Let me just go back to that. I should have mentioned that before. If I have a vertex V, by the total distance of V, I mean just the sum of the distances from V to all other vertices. And if I add these terms over all vertices, then I of course get almost the Wiener index, but to be precise, I would get twice the Wiener index because every distance would be counted twice. But that's not a point I want to dwell on too much. So what I'm interested in now is bounding the sum of the distances from V to all other vertices. And in this graph, in this picture, I've sneakily already put in the cycle because it will suggest something where our terms will be maximized. Okay, so if I just count how many vertices I have in each of these sets n1, n2, and 3, then I realize because my graph is too connected, n1 must contain at least 2 vertices. Otherwise, if it was only 1 vertex in here, removing this vertex would disconnect my graph because there's no way that I can get from V to n2 without going through a vertex in n1. Similarly, n2, n3, and 4, all of the following ni must contain 2 vertices. The only exception, the very last ni, can contain only 1 vertex because removing that one wouldn't be a cut vertex. So the total distance of V is now, well, a good way of calculating that is just count how many vertices do I have at distance 1 and multiply that at 1 by 1, plus how many vertices do I have at distance 2 from V, and I multiply that by 2, and then count how many vertices do I have at distance 3 from V, and I multiply that by 3. And that tells me that the distance of V is equal to the sum over all I of I times Ni, I times the number of vertices at distance I. And I've just argued that because my graph is 2 connected, each of these Ni must contain at least 2 vertices. So each of these little Ni must be at least 2, with possible exception of the last one and the first one as well. And subject to this condition that practically all Ni must be at least 2, it's quite easy to realize by just trying that this term, this sum over all I and I, is maximized if all Ni equal 2. So I get approximately that my sum is maximized if N1 equals N2 equals N3 up to equals Nk if they're all equal 2. So I wrote approximately because I ignored the possibility that the last layer may have 1 vertex. If we have k of these sets Ni of these layers, and if k is about n over 2, and all of these Ni are equal to 2, then we get that the sum of I and I is at most n squared minus 1 over 4 if n is odd, or n squared over 4 if n is even, if we do the calculations precisely. And then, if we do that, then we get that the distance of a vertex is at most the floor of n squared over 4. And now, adding this over all vertices, we will get the total sum, the sum of all distances. Dividing this by n choose 2, we get that the average distance of G is at most n times this term, n squared divided by 4, divided by n choose 2. And if you do the calculations, we get that this is at most floor of n squared over 2 divided by n minus 1, so about n over 4. Okay, so there's one more thing that I was quite keen to mention, and that's because I want to mention also some of the big problems here. So for the distance between any 2 vertices in a graph is, of course, can be any number between 1 and the diameter, the largest distance. So if I know the diameter of a graph, then I can immediately say that the average distance of a graph G is less or equal to the diameter. Well, it's clear. The average of all distances is less or equal to the largest of all distances. And of course, the average distance is at least 1. And Plesnik, that was really the first paper that went all out to explore mathematical aspects of the Wiener index and the average distance. He proved that this is really the best you can do. He says you can't say more, if you know the diameter of a graph, you can't say more than saying that the average distance is a value between 1 and the diameter. To be a little bit more precise, that's not quite all that he proved, but he said, okay, if you want a graph with given diameter, give me any number between 1 and the diameter, and give me a small epsilon. And that's epsilon like the people in calculus like taking it. So it can be an arbitrarily small number. He said, then I can give you a graph, G, that has diameter D, whose average distance may not equal to T, but it will be within epsilon of T. So for example, you want a graph with diameter 10 and average distance really close to square root of 2. Plesnik says that can be done. Maybe not equal to square root of 2, but as close to square root of 2 as you like. And it's good fun to try to prove that. The whole construction that he gave is a little bit complicated, but I find it quite enlightening, and that's one of the things that I suggest you could look at, is if you try to construct a graph with the following, that has the given diameter, let's say d, and the distance between almost every pair of vertices is equal to d. So in other words, if you pick a pair of vertices randomly in your graph, you can safely bet that their distance is equal to d. So almost all distances are equal to d. So it's fun to try to play around that. But these graphs that do that, they have usually a very large number of vertices. If we say we know about our graph, not just the diameter, but we also know the number of vertices, then things get incredibly, well, infinitely more difficult. And that's a big open problem that Plesnik raised in his paper in 1984. If you know the order and the diameter of a graph, what is the largest possible value of the average distance you can get? And that's a big open problem. To be precise, this problem is still open and people have thought about it. And just to give you an idea of how difficult this problem is, after years of trying, Delavinia and Waller in 2008, they said, okay, let's look at a vastly simplified version of this. If I tell you that I have a graph of order d, of diameter d and order 2d plus 1, is the cycle C with 2d plus 1 vertices the worst of those graphs? In other words, among those graphs with diameter d and 2d plus 1 vertices, is the graph among those with the largest possible average distance the cycle? And when reading this problem looks ridiculously simple, but it's still open, and I'm quite certain that people have tried to do it. However, there is a bit of good news, in fact, great news, because Stan Camby from the Netherlands proved a little while ago, not quite the question, but he solved it asymptotically. And that's like a gigantic progress in that. And he proved that the asymptotic maximum value for the average distance is at most the diameter minus, and I've simplified this a tiny bit, 1 over 12 times square root of 3 times d to the 3 over 2 divided by square root of n. So that's roughly what he did. And it was a very nice and short and sweet argument that he found. Lovely stuff. So let me just check how much time we've got. Ah, yeah, just a little bit of time left. Okay, just a little bit of time left for the last topic that I wanted to touch on. And as you have seen, I do like looking at distances in graphs and distances in diagrams. And there is one very natural way of connecting them, and that's looking at orientations of graphs. So let's say in the real world, we have the problem that in a town, we want to turn all streets one way to reduce number of accidents and improve traffic flow and all of that. But if we do it or if we don't pay attention and just do it in an arbitrary way, we may not even be able to get from every point in the town to every other point. But we also want to do it so that we don't have to do huge detours now, because out of a sudden, the shortest route from us to our favorite restaurant is just one-way roads in the wrong direction. So we generally want to try to also keep distances small. So in terms of graph theory, what does that mean? If we have given a graph G, if we to each edge, we assign an orientation. So we give each edge a direction, turn it into a one-way road, then we obtain what we call an orientation of G. So here's an example. Here's a graph G on the left and an orientation of G on the right. And of course, if that means we are now allowed to travel along edges only in the given direction. And that means distances may go up. So for example, the distance from the top left to the bottom right vertex in the graph is 2, but in the orientation of the graph, it out of a sudden becomes 4, because we first have to travel to the right, then down, down again, and then to the right. So distances, so if we take an orientation of the graph, distances may go up. In fact, things can get worse. If we orient a graph not cleverly, it may happen that we can't get from any point to another point at all. But even if we do it cleverly, there is one problem that we may run into it. That even if we look at all possible orientations, we may not be able to find an orientation of a graph that's strong, so that allows us to travel between any two vertices. For example, that's a big obstacle if a graph has a bridge. The edge here in blue. The bridge is an edge that if I remove it, my graph becomes disconnected. No matter how I orient my bridge here, there will be pairs of vertices that between which I can't travel. So let's say I assign the orientation from left to right of this bridge. Then, no matter how I assign orientations to the remaining edges, there will be no way that I can get from a vertex on the right-hand side of my graph to a vertex on the left-hand side. So if I orient my bridge the other way around, I will have the same problem. Just I can't get from left to right. However, so it may happen that there is no strong orientation of a graph. However, there is a classical theorem by Robbins, which says this is really the only problem you can run into. If your graph is connected and it has no bridge, then your graph is bound to have a strong orientation. And from here, I won't mention it every time, but we will only look at connected graphs that have no bridge. So usually people call this bridgeless graphs. And we are interested in distances. So we want to look at orientations that keep distances small. So let's say, in particular, we want to look at an orientation in which the diameter of the oriented graph is small. And for that, let's define the oriented diameter of a graph G. That's just the smallest diameter of an orientation of G. So in other words, the diameter I get if I take the best orientation that there is. Now that can be pretty hard. Finding the best orientation is a problem that is NP complete. That was proved in a classical paper by Quartal and Thomassen already for more than 40 years ago. But, well, if you can't solve a problem, or if a problem is hard for all graphs, there's always a point in looking at graphs from special graph classes. And for some graph classes, for example, for planar graphs, one can find a best orientation in polynomial time. Okay. But one question arises, and that was the big question that Carsten and Thomassen looked at and solved. And that was the question, if I have a graph G and the diameter of G is small, does this mean that the best orientation of G also has a small diameter? Well, let's be a little bit more precise. Is there a function f so that if I have a graph with no bridges of diameter d, then the oriented diameter of G is at most f of d? So in other words, I can find, is there a function f so that every graph of diameter d has an orientation whose diameter is at most f of d? Or is it possible that I can find a graph of diameter 5, for which the smallest orientation is as big as I like, 5,000, 5 million, 100 billion, whatever. And Quartal and Thomassen proved with a really nice proof that indeed such a function exists, and it's a function of the form O of d squared. So they proved if we have a bridgeless graph with diameter d, it has an orientation of diameter at most some constant times d squared. To be precise, they proved something like 2 times d squared. And the d squared is about the right term, because here's an example, which they provided, of a graph that has diameter d, but its diameter, its oriented diameter is approximately a half d squared. So imagine I put a vertex in the middle and I put this thing that looks a little bit like a tree on top, and the same graph that looks a little bit like a tree with a few extra edges at the bottom, symmetric. And this is really like long cycles that I put there that make it look long cycles that I have here. So clearly this vertex in the middle is quite in the center, and the distance from here, for example, to the top vertices is 3, to the bottom vertices furthest away is also 3, and its diameter is certainly 6, realized, for example, from this blue vertex to this blue vertex. Now, every strong orientation that I can find will have to orient these things that look like big triangles, like cycles. And I've indicated with the blue drawing here that I think of these now oriented in a clockwise order. This is the up to isomorphism, the only possible strong orientation of this graph. But then out of a sudden, the distance from the blue vertex here in the top left to the blue vertex, the bottom left, goes up, because the shortest path will have to first go through the first little triangle, then go through the bigger triangle, then go to through the biggest triangle, then continue through the biggest triangle, go through the smaller triangle, and it has to cover a lot more vertices. So this very nice example shows that d square is about the right order of magnitude. But the big problem, and that's really a big problem, is determine the smallest function f that does the job. In other words, determine the smallest f so that every graph of diameter d has an orientation whose diameter is at most f of d. And Quartal and Thomassen proved that this f of d is always between about half d squared and 2d squared. To determine the precise value of f, however, is extremely difficult. So in their classical paper, they proved that f of 2 is 6. So every graph of diameter 2, bridgeless, has oriented diameter equals 6, and the graph that shows that it is equal to 6 is the Petersen graph. You won't be able to find an orientation of that whose diameter is less than 6. And that suggested to a few people, well, let's try to determine f of 3, but it took people after, and a few papers have appeared on that, about 40 years to prove that f of 3 is probably equal to 11. And I wrote a question mark because this actually I saw in a paper which hasn't appeared yet. So it still has to be checked and verified. So there is a little bit of movement in this. And there's another bit of really great news, because the group from India, Babu, Benson, Rajendra Prasad, and Vakha, proved just this year the Thomassen's and Quartal's bound, upper bound, from 2 times d squared to about 1.3 something times d squared. So that's a significant improvement. However, as I said, determining this value of f, the precise value, is extremely difficult. There are linear bounds for some special graph classes like interval graph and other things, but the general problem remains extremely difficult. So let me see, there are these things I wanted to skip in the interest of time. So you've seen there is still quite a bit of work to do and quite a few mountains to climb if we want to make headway. And one of the more beautiful ones I've shown on my last slide. And with that, I would like to thank you. So yeah, thanks a lot for the question. So if we have two graphs, G1 and G2 with diameter D1 and D2 respectively, can anything interesting be said about their Cartesian product? Yes, indeed. Indeed. The diameter of the Cartesian product will be exactly D1 plus D2. So it's completely determined by D1 and D2. And for other graph operations, yes, if you take the strong product, for example, the diameter will be the maximum of D1 and D2. And for other graph products, I would have to think. If you take the join, the diameter will be like D2. Other things I have to think about. But yes, interesting things can be said. I hope that helps.